All right, we're going to start chapter 2, which deals with polynomial power and rational functions. So functions we dealt with a lot in Algebra 2. This one may seem a little new, but it's actually a pretty simple version of a polynomial function. The first section deals with just linear and quadratics and modeling with them. You can take a look at these objectives if you'd like. As you go through them, you're going to realize it's a lot of stuff that we did in multiple chapters in Algebra 2. We're just going to kind of combine it all together in one little section in Honors Math 4. So we're going to start with the definition of a polynomial function, which has a standard form right here. The main thing that we want to look at is what the degree of that function is. The degree is n, which is this value right here, the highest exponent on one of the single terms that we have. And n has to be a whole number in order for it to be a polynomial function. So as we look at the 5 examples down below here, we have some that are and some that are not polynomial functions. The first one is a polynomial function. It's just not in standard form because this is actually our highest power there. We can still identify the degree as being 2. And they also ask us to do the leading coefficient as well. The leading coefficient here then would be the -5 that is in front of the x squared. The next function there is not a polynomial function because of the square root. The third function is a polynomial function. It is in standard form. The degree is 4, and the leading coefficient on that same term is 2. That fourth function, g of x equals 6, is a line. It's like y equals 6. That is a function. It's a constant function. When the degree is 0, because we have really, if you want to have x here, you'd have to have it to the 0. When the degree is 0, then the function is a constant polynomial function. We don't have to call anything a leading coefficient because we just have a constant there. And then the last function, oh, that's kind of hard to see, that says 2/3 right there. The last function, because it does not have a whole number exponent, is not a polynomial function. So I'm just going to write this is not a whole number, which means it's not a polynomial function. As we just stated, polynomials with degree 0 are actually called constant functions, constant polynomial functions. All right. If this could work, that'd be awesome. I just wanted to be able to have you guys be able to read this. So this is a constant polynomial function. The next one here with degree 1 would be a linear polynomial function, and the third one would be degree 2 quadratic. All right, we've done regression this year already. I think it's a good idea to just review it as we go through the different chapters here. So we're given the relationship between calories here, and the grams of fat in 9 different hamburgers from various fast food restaurants. So we're going to put in calories as list 1 and grams of fat as list 2 in our graphing calculators. Okay, so take a second to do that. Pause the video if you'd like to throw that in your graphing calculator. Hopefully when you are done, it looks a little something like this. In order to do the regression, we first should make sure that we look at the data. It tells us to do a linear regression, but I'm just going to look at the data here, a scatter plot, to make sure that it is somewhat linear. So once you got this in, we want to just go to our stat plots, turn one of them on, probably the first one if you're only doing one. So I'm going to turn it on, make sure it's on scatter plot, make sure we have list 1 and list 2 as our two lists, as our independent, dependent variables. And then we want to graph it. Remember, if we just hit graph, we could be anywhere in our graph calculator or anywhere in our window here. Right now I'm on the standard window. So our quick way to get to our data is to hit zoom and number 9, which is zoom stat. And it'll go right to your data. Okay, so assuming that I plugged this data in correctly, I'm just going to take a look at it one more time real quick to make sure that I had that put in correctly. Let's see here. All right, so I'm going to go back to my home screen. Just quit out of this. It looked somewhat linear, so I'm going to do the linear regression by going to Stat, Calculate. We want to do either number 4 or number 8 if we're doing a linear regression. I'm just going to stick with number 4. Make sure you have L1 and L2, and then of the utmost importance, first of all, make sure your frequency list is empty. We don't need that right now. We want to make sure that it puts the equation somewhere that it'll graph the line. So we want y sub 1 for that. So we're going to put y sub 1 right here. If you have an older calculator, it takes you a little bit longer to get to that. If you need help with that, let me know. You should have a regression sheet. I think it was bright blue this year that reminded you how to find these things and how to put data in. But we're ready to calculate this now. Okay, so this will give us the actual equation there. A and B are our slope and y-intercept, respectively, because remember, the regression that I picked had it in the form y equals ax plus b, which is the same as mx plus b. So a is the slope. So I'm just going to write here this as a function. The fat, given the number of calories, is equal to, I'm going to round to the thousandths here and say 0.071 minus 9.268 C. Okay, if you're taking a AP Stats class, or if you plan on taking it, I'm just going to show you what that would look like in a stats class. We often just use words as our variables. So I'm going to have fat equals negative 0.92, and I'm going to flip it around too, because a lot of times we do this in stats. This is what would have been what linear regression 8 would have given us, oops, in this order, with the y-intercept actually first, and then the slope. And I'm going to multiply that by the calories. So like I said, in a stats class, oftentimes we use just the words as our variables. And then you'll notice that guy right there, that just means predicted. So the predicted fat would be given to you from this expression right here. Again, this is what you would see in like an AP Stats course. I know some of you have taken that this year. Just so you see, it really is the same thing, just written a little bit differently, a little bit different notation. One of the reasons why we put our equation into y sub 1 is so that we can answer question B using our calculator. And the reason why it says do not round, that doesn't mean your final answer. We're going to round our final answer if we have to. Obviously we're not going to not round it. What that means is we don't want to use this equation with the rounded values in it. We're going to use our graphing calculator that has digits stored much further than just to the thousandth. So to do that, I'm going to quit out of here. We could actually go back to the graph, and we could do second calculate. I'll show you that here in a second, once that's done graphing. Second trace goes up to the calculate menu on the graph and do a value, number 1. And we want to find the amount of fat in a hamburger that has 475 calories. So I'm going to find the value of 475. There you go. 24.651. So that's one way that you could do this, is on the graph. Okay. Another way that you could answer this question is using that equation that you had as if it were a function, and find f of 475 just using your y sub 1 in your graph calculator. So I'm going to second quit and get back to the home screen. I'm going to grab y sub 1 alpha trace. Number 1 is y sub 1. And just like function notation, I'm going to tell it to put in 475 as an x value. And that's going to give me that same value of 24.651. So it's about 24.651 grams. All right, so that is another way that we could answer that problem, is by using the, oops, I'm not sure why it's doing that. By using the actual function that we had typed in. That's one reason why we had it saved where we did. So to answer that last question there, thinking about what it means in the context of the problem, what the slope means, that would be remembering that slope is a rate of change. It's change in y over the change in x, or delta y over delta x. Well, in this case, y is fat and x is grams. So this is kind of what your thought process is as you're writing this. So we're going to write something to this effect here in order to explain what the slope means in the context of the problem. In general, each increase by 1 calorie, so that's saying by each change in g, so I'm kind of explaining what the denominator means, by 1 calorie results in an average increase, slope is the average rate of change, of about 0.071 grams of fat on average. That's what that slope means. All right, a little blast from the past here, working with quadratic functions. We're going to graph a quadratic function that's in vertex form. Vertex form, remember, is this form here, and we know that hk gives you the vertex of the parabola. But we also want to talk, relate this to what we've talked about already in Honors Math 4 and talk about the transformations done on the graph here. So the parent function is y equals x squared. All right, so I'm going to come over here. I know that my parent function table then would be 0, 0, 1, 1, 2, 4, 3, 9, so on and so forth. I'll go one more there. What we know is going to happen to this graph, though, and we should talk about stretches and reflections first. So I see that right there is a stretch. That's our A value. That is a vertical stretch of 3. We also have a shift from that plus 5 right there, left, not left, left 5. And we also are going to go down 2. Okay, so that's really what's happening to the function. In order to graph it, quickly, what we do is we actually just go to that vertex of hk, or what we did in algebra 2 is we went to that vertex of hk, or in this case -5, -2. So I'm going to write that as well here, that's our vertex. -5, -2, and we basically use that a value of 3, and we changed our table to reflect that that is what the stretch is going to do to it by multiplying all the y values by 3. So our x values would stay the same. We're going to multiply our y values by 3. So I'm really not going to get many of these on there. What's 16 times 3? 48. There we go. Okay. Now, if you're going to use this method, this needs to come from the vertex. They are not actual points in the graph. For example, the point 212 is not going to be on our graph. It's from the vertex. I'm going to go right to up 12. So if I graph this vertex first at -5, -2, just going to put -5 on here. 1, 2, 3, 4, 5. Go down 5 this way. Just get some of this marked off. Okay, so if I go left 5, down 2, it'll be about right there. And then I'm going to graph from that point the points from that table right there. So I'm going to go over 1, up 1, 2, 3. I'm going to reflect that right away over the axis of symmetry. I'm going to go over 2, up 12. Somewhere up there. Reflect that. That's pretty good. We know that it's going to be a pretty narrow graph. Right? Now this is not, I'm reminding you of how we did this in Algebra 2 because it's quick, it's efficient. Now the way that we've been graphing it this year so far is by putting all of that into a table, which you could still do. I have no problem with that. Then our table would have looked like this. We would have said, and we would have gone from the origin. We would have said to our x values, since we're going to go left 5, we'd have to subtract 5. And to our y values, we're going to stretch them by 3, but we're also going to move them down 2. So we'd have to take all of those x values and y values from that table, put them through the ringer in these expressions right there, and come up with our new values. Okay, so for all my x values, I just subtracted 5 and got -5, -4, -3, -2, so on and so forth. I think the last one would be -1. And then I'd put all these y values here into this guy. So we'd have 0 minus 2, I'd have 3 minus 2, I'd have 12 minus 2, which is 10. I'm just going to stop right there. Now these, if you want to do it this way, these then would be from the origin. Okay, these are actual points that are on the graph. -5, -2, that's the vertex. -4, 1, that's that point right there. Okay, so I don't care which way you do it. You can use what we've used this here with transformations, or you can be a little bit quicker. I like to use the word efficient, sounds better, and just go from the vertex and use your A value. All right, one of the big things that we need to know is how to find the vertex if we are given standard form. Standard form is ax squared plus bx plus c. So the main idea that you need to know is that. And according to Ms. Hughes, our calculus teacher, that is one thing that a lot of our calculus students tend to forget once they get to her class. So make sure you know, or make sure that you should know that that's expected. You know how to find the x value of a vertex, -b over 2a. It shouldn't be hard to remember because that is a small part of the quadratic formula. We are going to skip example 4 there. If we have time, we might look at that in class. But that is, it's not necessary to help us complete our examples here. It's just kind of a fun thing to do. So let's look at example 5 here. Wants us to find the vertex first. So we're going to use -b over 2a to start. So x would be, -b over 2a would be +6. Opposite of b over 2a, a is 2, so 6/4, which is 3/2. To find the y value of the vertex, then you have to put that into the function. So y is going to be f of 3/2, which is going to be 2 times 3/2 squared minus 6 times 3/2 plus 11. And with a little math magic, you should end up finding out that that's 13/2. So our vertex, we know, is 3/2, comma, 13/2. That's our vertex. All right. Now that's one way to find the vertex. Another way to find the vertex is completing the square. So we're going to run through that too. We should come up with the same vertex. What that's going to do though is put it into vertex form. So let's remind ourselves that to do this, we need to pull out the 2 because you have to have that just being x squared. So we've got to pull that 2 off of just really those first 2 terms. Okay, I'm just going to leave a space there so I can actually complete the square, and I'm going to shove that plus 11 just out of the way. I know it looks weird. It looks like we're kind of cheating by only pulling the 2 off the first 2 terms, but if I distributed this through, I have the same function as I started with, so we haven't really changed anything. Now we can complete the square the way that we have in the past. We know that this is going to factor to some binomial x, and then we take half of that right there to get -3/2. And then when we go back up here, we square that, so plus 9/4. Now remember, when we complete the square to solve, what you do to one side, you do to the other. So I could add 9/4 over to this y over here, but I want this thing to say y equals. I don't want it to be y plus 9/4. So right away, I'm going to keep everything on the right side and subtract 9/4 from the same side. Okay, so again, I haven't changed anything. If I got a common denominator, I have 44 over 4, that's the 11. 44 minus 9 is 35. Oh, I almost missed an important thing here. I'm so glad that happened. I like to make mistakes, not on purpose. I'm not saying I did that on purpose, but I like to make mistakes here so that you can point it out and say, don't make that mistake. Remember, everything inside that parentheses is being multiplied by by 2. So if I'm multiplying that 9/4 by 2, or what I'm really adding is 9/2 there. So to combat that, to negate that, I have to subtract 9/2. I forgot to multiply it by that 2. So we actually need to take 11 minus 9/2. So what I have is 22/2 minus 9/2, which is 13/2. Okay, that's pretty crucial. And what you see here is vertex form. I'm going to write it a little bit nicer here. 2 times x minus 3/2 quantity squared minus 13/2. Notice we have our vertex in our HK spot, 3/2 comma negative 13/2. All right, now we're going to use A as our vertical stretch here. No matter which way you use to find the vertex, I'm going to now just use A from my vertex. So just as a reminder, if we were at 0, 0, we would have our parent function 0, 0, 1, 1, 2, 4, 3, 9, so on and so forth. But from HK, what I want, I have no idea why I put the 0 up there. 0, 0. Here's x and y. Sorry about that. From HK, remember, we want to take into account what our A value is. Our A value is 2. So we're going to stretch the y values by 2. So I'm still going to keep those same x values, 0, 0, 1, 2, 3. But now my y values are going to be 0, 2, 8, and then 18. And again, these come from the vertex. You have to do that from the vertex. Okay. Now we started in standard form. So another thing that we have from standard form is the y-intercept. Okay, that doesn't show up in vertex at all, but we do have it from our standard form. So it's kind of nice to have it in multiple forms, because you can use a couple different pieces of information. So start graphing this guy here. Okay, so I know my y-intercept we just said is 11. I'm just going to put that on the graph right away. We said our vertex is 3/2, negative 13/2, which is negative 6.5. So not negative. Why do we have a negative there? Why do I have a negative there? This should have been positive the whole time. If I could, I would do this whole video over again, but I don't have the time to. So we're going to keep going with where I am here. I'm sure a lot of you have already caught that mistake and fixed it. Good for you. Let's move on. So I've got 3/2, which is 1.5, which is going to be right there. So actually, what I know, and you don't have to draw this if you don't want to, but I know that there's an axis of symmetry right there. If we asked you what the axis of symmetry is, you would know that it's the line where x equals 3/2. These values are always the same. Axis of symmetry goes right through the vertex. And then our vertex's y value is 13/2, which is 6.5, which is about right there. Now from that point, I'm going to use that table right there. I'm going to go right 1, up 2, reflect that. I'm also just going to reflect my y-intercept over. There it is right there. And then I'm going to go over 2, up 8. 1, 2, 3, 4, 5, 6, 7, 8, about right there. And we have a pretty good idea of what this graph looks like. It's narrower than the parent function because of the vertical stretch of 2. All right, this is a good chance to stop and make sure that you go fix all the mistakes that I made, fix those in your notes, and then we'll start the rest of it in a second video.